So welcome back everybody. Today we're going to continue with our lecture on quantum mechanics, and in this video we're going to go over some examples of problems that we can solve using the Schrodinger equation. So the first case that we're going to look at is this, a 1D particle in a box. So here's what's going on. Let's consider a particle that is free to move within some region of space of length L, but it cannot go outside of that region. So in other words, we have a particle. It can only move in one dimension along a line, and it's restricted to a line of length L, and it can't go outside of that region. So we can set the potential energy for this particle in the following way. We can say U of x is equal to 0 in between x equals 0 and x equals L. So that's the region where the particle is free to move around in. But if we want to say that it's impossible for the particle to go outside of that region, we're going to set the potential energy to infinity everywhere else. So if we plot this out, it looks something like this. We have our potential energy going on the vertical axis this way, and x going on the horizontal axis this way. So again, the potential energy is just 0 everywhere between x equals 0 and x equals L, but then it blows up to infinity all of a sudden once you hit those boundaries of the box. So that's the situation we have. So the question is, what type of wave function would we expect the particle to have in this box? Well, we can say that we expect a free particle wave function when we're in between x equals 0 and x equals L. And that's because, remember, for a free particle, there's no force acting on it. And that's the situation we have when the particle is within this box. As far as outside of the box, we expect the wave function just to be 0, because remember, the wave function gives you the probability of locating the particle within a certain region. And if we're saying the particle cannot be located outside of the box, like over here or over here, well, then the wave function has to be going to 0. And actually, that sets a nice boundary condition for us. We can say that the wave function, psi, whatever it's doing, once it reaches x equals 0, the value of the wave function has to go to 0. And then the same applies for x equals L. The wave function at x equals L also has to be 0. Again, that's because the probability of finding the particle outside of the box is going to 0. All right, so with that said, we have some sense of what the wave function should look like, but let's explicitly solve for the wave function of this type of particle and see what it looks like. So we can say something right off the bat about what the solution should look like for the region x equals 0 to x equals L. And basically it's this. It's a sum of free particle solutions, which we went over in the last video, for motion in the positive x and negative x direction. So we don't want to say that the particle has to be moving in the positive x direction or it has to be moving in the negative x direction. We're just going to allow for the possibility of either type of motion within the box. And so if you recall, what this looks like is we have lowercase psi of x, that's the time-independent part of the wave function. That equals a times e to the ikx. That's our solution for the positive x direction. And then I'll say plus b times e to the minus ikx. All right, so that's what it looks like when we have a sum of free particle solutions for motion in the positive and negative x direction. Okay, so the next thing I'm going to do is apply Euler's identity. So remember from the last video that we can write e to the ikx as a sum of cosine and sine terms, just like this. So the first term I'm going to write as a, and then we have cosine kx plus I sine kx. Okay, so I'm just applying Euler's identity that I showed you last time to the first term. The second term is b times, okay, now instead of kx, we have minus kx going inside the cosine and the sine function. So we have b times cosine minus kx. And then we have plus I times sine of minus kx. Okay, so I'm going to leave the first term alone, but I'm just going to sort of copy it down for reference. Same as before, a times cosine kx plus I sine kx. For the second term, I'm going to rewrite this. So we have b times, and then in the brackets, cosine of negative kx. Okay, so the cosine of the negative of some angle is the same as just the cosine of that angle. So in other words, cosine of minus kx is the same as cosine of kx. That's just a property of the cosine function that you should know about. With the sine function, it works in the opposite sort of way. So the sine of minus kx is equal to minus sine of kx. So I can write this last term as minus I times sine of kx, just like this. Okay, so there it is. That's what we get when we apply Euler's identity to our wave function. So now let's apply the boundary conditions. And there are two of them. The first one is this. We know that psi at x equals 0 is supposed to equal 0. Okay. So let's plug in 0 for x in the wave function we just wrote down. What we get is a times cosine 0 plus I times sine of 0. And then plus b times cosine of 0. And then we have minus I times sine of 0, like this. All right, let's try to simplify that. Cosine 0, that's just equal to 1. Sine of 0, that's equal to 0. And that's also true over here. So what we have is a times just 1, and then plus b times also just 1. And we're saying that has to equal 0, right? So what that tells us is that b is actually just equal to minus a. So by applying the first boundary conditions, we were able to come up with the fact that this constant b in our wave function is just the negative of the constant a in our wave function. Okay, so let's actually write down what our wave function looks like now that we know this. Now we have psi of x equals a times cosine of k times x. Oops, let me rewrite that. So it's a times the cosine of k times x, like this. And then plus I times sine of kx. And then we have minus a. So over here where I see a b, I'm just replacing that with minus a. And then we have in those brackets cosine kx, and then minus I sine of kx. Okay. I'll try to simplify that a little bit. Let's actually collect all the terms that have a cosine multiplying them. So let's just say cosine kx. Well, from our first term, we have a factor of a. And then from our second term, we have a factor of minus a. If I do the same thing with the sine terms, I have sine of kx. Okay. Then from my first set of brackets, I have I times a. And from my second set of brackets, well, I have negative a, negative I. So those two negative signs cancel. And that's just another I times a factor. So overall, actually, if you look at the first term, it's got to equal 0 because you have a minus a, which equals 0, multiplying the cosine. So that just goes away. And what we are left with is this. 2 times a times I times sine of kx, which is not too bad. That's a pretty simple form. Okay, so that's what our wave function looks like so far. But we haven't yet applied our second boundary condition, which says that psi at x equals L is equal to 0. So let's do that. So what happens when I take my wave function in the sort of simplified form we have it in over here and plug in x equals L? Well, here's what I get. I get 2 times a times I times sine of KL. And we're saying that has to equal 0. Okay. So what really this is saying is that the sine of k times L has to equal 0 because everything else is just a constant out front. Okay, so the question is, what angle can I plug into the sine function and get out 0? Okay, well, if I do k times L equals 0, that would work, right? Because the sine of 0 is equal to 0. If I had pi, that would work also because the sine of pi is equal to 0. 2 pi would also work, 3 pi, and you can probably see where this is going. The general trend here is that k times L is going to be equal to n pi for n equals 1, 2, 3, and so on. Now you're probably wondering, don't I want n equals 0 to be part of this? What about n equals 0? Shouldn't that work? Well, the problem with that is if n is equal to 0, okay, then we're saying k times L is equal to 0. Then our wave function is just 0 everywhere, right? And we don't want that to be the case. So the wave function being 0 everywhere just means there's not even a particle there. So we're going to exclude the n equals 0 case. Okay. So what we're left with then is this. We're saying k times L is equal to n pi. That means k is equal to n times pi over L. So only these specific values of k can work. Okay, so we're almost there. We should probably just kind of take a look at what we have so far. What we have is psi of x is equal to 2 times a times I times sine of kx, but we're saying k is equal to n times pi over L, and then that's multiplying x like this. And this is true for n values, starting at 1, 2, 3, and so on. So basically all the integers. There's one last thing we have to do. We have to figure out what is this constant out front. And in order to do that, we're going to apply the normalization condition. Remember, our wave function has to be normalized. If we integrate the wave function squared over all space, we should be getting 1, okay? So now what we're going to do is apply the normalization condition. And I'll just write the general form of the normalization condition. Okay, this says that if you take your wave function and integrate between minus infinity and infinity of the wave function squared times dx, that should equal 1. Okay, so what does that integral look like in our case? Well, in our case, here's what we have. We actually only need to integrate between 0 and L, because like we said, the wave function is 0 everywhere else. And let me actually also remind you, when we say the square of the wave function, this is what we are really talking about when it comes to complex numbers. We're talking about taking the complex conjugate, psi star, of the wave function times the wave function psi, and integrating that. And that's what's equal to 1. So we have to worry about this because there's an I appearing here. We have to worry about this whole complex conjugate thing. So anyway, the way the complex conjugate works is you just replace every instance of I with negative I. So the complex conjugate is like this. We have 2 times A. Sorry, let me rewrite that. It's minus 2 times A times I times sine of n pi x over L. And actually, I'm going to do one more thing to this. Instead of A, I'm going to write this like A star. Because technically, A could also be a complex number, and I need to be taking that complex conjugate as well. All right, and then we multiply that just by the wave function itself, which is just 2 times A times I times sine of n pi x divided by L. And then that's multiplying dx. All right, that's great. So let's see what we have. I have minus I times I going on here. There's a minus I here, there's an I here. And minus I squared, which is what we have here, is equal to minus -1, because I squared is -1, so this is just +1, all right? So we can get rid of all the I terms and just get rid of the negative sign all at once, because again, minus I squared is +1. Then we also have 2 times 2, which is 4, and that's a constant we can pull out. And then we have A star times A, which we can pull out. Those are also constants. And then what we're left with is this, the integral from 0 to L of sine squared n pi x over L. Okay, so it's not that bad to integrate sine squared. I just want to skip over that for now and just tell you what the result is. Okay, so we have 4 times A star A, which I could write as A squared. And I'll just tell you that this sine squared integral works out to L over 2. That's the result. Okay, so what do we have overall? Looks like we have an overall factor of 2, then the A squared, and then the L. And in order for this to be normalized, okay, so for the wave function to be normalized, that whole thing right there has to equal 1. So 2 times A squared times L is equal to 1. So what does that mean? It means A squared is equal to 1 over 2L. All right, so what could A be equal to in that case? You're probably thinking just take the square root and that's it. But I'm going to write A like this, which may seem a little weird, but you'll see why I'm doing this in a second. I'm going to say A is minus I times the square root of 1 over 2L. Now, remember, A could potentially be a complex number. All we know is that A squared is equal to 1 over 2L. And remember, when we say A squared, when we're dealing with complex numbers, that means A star times A, right? So in this case, A star would be plus I times the square root of 1 over 2L. And A is just minus I times the square root of 1 over 2L. Again, we have plus I times minus I, that just equals 1. And then we have the square root, which we have 2 copies of, so square that, and you get 1 over 2L. So I'm just showing you that this works, okay? And it's useful to define A with the complex number I out front, because if we scroll back up here, remember, this is our wave function. So I'm going to plug in that value of A into the wave function, and you'll see that psi of x is equal to 2 times A, which is minus I times 1 over 2L under the square root. And then that's multiplying I, and then that's multiplying sine of n pi x over L. Okay, so we have minus I times I in this thing, which is just equal to 1. So that means we can write this as just 2 times 1 over the square root of 2L like this, and then sine of n pi x over L. And we can actually bring that 2 inside of the square root, and it will look like this. We have the square root of 2 over L times sine of n pi x over L. And that's the result I wanted to get to. So n, remember, can take on various values, integers, 1, 2, 3, and so on. So this actually gives you a whole range of potential wave functions that the particle could have, because you can have any potential value of n being plugged in there, right? So the last thing we're going to do is we're going to plug this wave function into the Schrodinger equation. And by doing that, we can solve for the energies that are associated with these various wave functions. So remember, here's what the Schrodinger equation says. We have minus h bar squared over 2m, multiplying the second derivative of our wave function with respect to x. And then we add the potential energy times our wave function. But remember, in this case, the potential energy is just equal to 0. And that's equal to the energy of our particle E times the wave function. Okay, so what we can do is plug in the wave function that we just solved for into this equation. All right, so we have minus h bar squared over 2m. And then I'm going to write this in brackets. We have the second derivative of our wave function. So remember, our wave function is a sine function. And then there's a constant of root 2 over L out in the front. Okay? If we take two derivatives of this function, each time we take a derivative, we're going to pull out a factor of n pi divided by L. But also, when you take the derivative of the sine function twice, you just get negative sine. Okay, so overall, here's what we have. We have minus, we have n pi over L squared, because we get a factor of that each time we take a derivative. And then we have sine of n pi x over L. Okay, so there it is. There's the second derivative shown in the brackets. And then again, the potential energy term was 0, so then this is just equal to E times the wave function itself, which I'll just write in brackets as root 2 over L times sine of n pi x over L. And let's cancel some things. We have the root 2 over L on both sides going away. And then we have the sine of n pi x over L on both sides going away. On the left side, we have two negative signs, which cancel out. And on the right side, we just have the energy all by itself. So actually, we can solve directly for the energy. If we solve for it, we'll find that E is equal to, we have on top h bar squared, pi squared, and an n squared. On the bottom, we have 2 times m, and then L squared. All right, so that's a nice expression for the energy. So we did two things here, the two results in boxes. We have all of the possible wave functions for a 1D particle in a box and the associated energy values alongside that. And so here are the results that we just came up with to summarize. We solved the Schrodinger equation and we found all possible wave functions and the corresponding energy levels for this 1D particle in a box. For the wave functions, which we're going to label as psi sub n, we have the square root of 2 over L times sine of n pi x over L. And you can plug in any integer value with n, from n equals 1 to 2 to 3 and so on, to get a valid wave function. For the energy levels, which I'm going to write as E sub n, we had pi squared times h bar squared times n squared, all divided by 2 times m times L squared. So what I'm going to do is separate out the n squared from the rest of this stuff, because all the stuff over here is just a bunch of constants. And we're going to call those constants all lumped together E1. Because if you think about it, that's the energy that you get when you plug in n equals 1. And actually, we call that the ground state energy, because it's the lowest possible energy level. It's not possible to go lower in energy than E1. And also notice that it's not possible for the particle to have 0 energy. E1, the ground state energy, is actually the lowest possible value. And to get all the other possible values, you're just taking E1 multiplied by n squared, where again, n is this integer value. So we're seeing, once again, that the energy levels are quantized. This is something we see a lot in quantum mechanics. They can only take on certain discrete values with gaps in between. Okay? And let's go ahead and look at plots of the wave functions for the first 4 energy levels. So n equals 1, n equals 2, n equals 3, and n equals 4. So let's plot those out. For n equals 1, our wave function looks just like this. It's a sine wave with a single loop. Okay, that's what's shown in blue. For n equals 2, it's a sine wave with 2 loops. For n equals 3, that's the one in green here, it's a sine wave with 3 loops, and n equals 4, same thing with 4 loops. Notice that these wave functions are exactly like the standing waves on a string that we saw way back in, chapter 16? And the reason for that is the wave function is fixed at both ends, just like a string on a guitar or something like that is fixed at both ends. We're saying that the wave function has to go to 0 at x equals 0 and x equals L, just like a wave on a string has to have nodes at x equals 0 and x equals L. So interestingly, some of that math from before is coming into play here. And one last thing to note is when we plot out psi of x, this is the time-independent wave function, we're just showing what a snapshot of the wave looks like at one moment in time. Okay, if we incorporate the time dependence of the wave function, we'll see that it's actually this shape, but oscillating up and down at some frequency. Okay, so I just want to remind you that these wave functions are actually going to be oscillating at some frequency omega, where this omega is related to the energy in this way. E is equal to h bar times omega. And actually, let me just show you what that looks like when we animate the wave functions. We don't just show a static image of the wave functions, but we let them move in time. So here we have the n equals 1, 2, 3, and 4 wave functions that I showed you before. And I'm only going to show you the real component of the wave function. So that's what's going to be on the vertical axis. And let's just play these animations, see what they look like. So again, it looks exactly like a standing wave on a string. It has a single loop in the n equals 1 case, and the wave just oscillates up and down like this. Okay, same for the n equals 2 case. It's exactly analogous to the standing wave on a string. Here's the n equals 3 case, and here's the n equals 4 case. So notice, the higher the energy, the faster our wave function oscillates. That's something we saw before. Okay, so in the lowest energy state, the wave function oscillates slowly, and as the energy goes up, it oscillates faster and faster. Because remember, the energy is directly proportional to the frequency that it's oscillating at. So the higher the energy, the faster the oscillation. All right, so next we're going to take a look at expectation values for position and for momentum for this 1D particle in a box. So remember, if we were to take a measurement, let's say, of the particle's position, the outcome of that measurement would be completely random. We never know in advance what we're going to get. However, the wave function tells us the probability of different measurement outcomes. So if I take a lot of different measurements of the particle's position, sometimes I'll find it over here, other times I'll find it over there. But what I can do is take an average over many repeated measurements. And the expectation value is just the average of many repeated measurements. So if we want to calculate the expectation value for the position, that's given by x in the brackets here, that is the integral from minus infinity to infinity of x times the square of the wave function dx. So if you do this integral, you're going to get L over 2. I'm not going to work this integral out right now, but the result of this is L over 2. And that's for any value of n. So we could be looking at the wave function for the n equals 1 state, we could be looking at the wave function for the n equals 2 state, or whatever, and we would always get L over 2. And what that's telling us is that on average, the particle is in the middle of the box. It doesn't have a preference to hang out on the right side of the box or the left side of the box. On average, it's just in the middle. We can also do the expectation value for momentum. And this is what we call P with the brackets around it. So we can calculate this by taking the integral from minus infinity to infinity of P times psi P, so this is the momentum space wave function, squared times dp. Again, I'm not going to work this integral out, but you can show that the result of this is 0 for all values of n. So what does it mean for the expectation value of momentum to equal 0? It doesn't mean that the particle is not moving. It actually just means that it's equally likely to be moving to the left or to the right. So in other words, it's equally likely that it has a positive momentum or a negative momentum, so that on average, it just has 0 momentum. So let's take a look at an example here. A simple model of an atomic nucleus treats each proton as a particle in a 1D box. The typical size of a nucleus is about 10 to the minus 14 meters. So the picture we should have in our minds is this. The proton is free to move around within the nucleus, but it can't go outside of the nucleus. And the length of that region that it's confined to is 10 to the minus 14 meters. So with that said, what are the energies of the ground state, that's the n equals 1 state, and the first excited state, that's n equals 2, for this proton? And we're going to calculate this in units of MeV, that's mega electron volts. Okay, so the next question is, if the proton makes a transition from the first excited state to the ground state, what is the energy and the frequency of the photon that it has to emit? We're going to give that in units of hertz. Okay, some numbers you might need to know. Planck's constant is given right here. The reduced value is given here. And the mass of a proton is given here. And then also, this is the conversion between electron volts and joules. You might need that. And then lastly, you might need this formula right here, which gives us the energy levels for our particle in a 1D box. So pause the video, try to work these out, and then we'll go through it together. So we'll start by calculating the ground state energy, that's E1 for this particle. And E1 is equal to pi squared times h bar squared over 2m times L squared. That's the ground state energy for a particle in a box. So let's plug in what we know. We have pi squared. Okay, h bar is the same as 1 over 2 pi times h, and then h is 6.626 times 10 to the minus 34. And the units here, if we go over that, are kilograms meters squared per second. And we're going to square h bar. Okay, then we're going to divide out. We have 2 times the mass, so we have to plug in the mass of a proton here. That's 1.67 times 10 to the minus 27 kilograms. And then L is the length of our box. So that's going to be the size of the nucleus, which is 10 to the minus 14 meters. And we'll square that. Okay. So this comes out to 3.286 times 10 to the minus 13. And let's think about the units here. It looks like we're going to end up with kilograms, and then meters squared divided by seconds squared when it's all said and done. So that's equivalent to joules. So what we should do is convert joules to MeV. So we have 3.286 10 to the minus 13 joules. And remember that 1 electron volt, 1 eV, is the same as 1.602 10 to the minus 19 joules. And so this works out to 2.051 10 to the 6 eV. And remember, 10 to the 6 is the prefix mega, right? So this is the same as 2.05 MeV, mega electron volts. Okay, so that's the energy of the ground state. Now, remember that the energy of any other state, we'll call it E sub n, is just E1 times n squared, where remember n has integer values, 1, 2, 3, and so on. We want the energy of the second levels, that's E2. And so what we get is E1, 2.051 MeV, multiplying 2 squared, right? Because that's n squared. And this works out to about 8.0, sorry, no, it doesn't. That's 8.204 MeV. Okay? And we'll round that to about 8.20 MeV. So those are the two energies for the ground state and the first excited state. So to answer the next question, we're imagining that the proton transitions from the n equals 2 state down to the n equals 1 state, so it loses energy. If it's going to do that, it's going to have to give off a photon, which will carry away that energy. So the idea is the energy of the emitted photon that's equal to the energy lost by the proton. So this is how we sort of apply conservation of energy to this situation. So the energy of the emitted photon, I'm going to call that E gamma. And so E gamma should be equal to the difference between energy level 2 and energy level 1. So E2 minus E1. So this gives us 8.204 MeV minus 2.051 MeV, which works out to 6.153 MeV or 6.15 MeV to round it off. So that's how much energy this photon is carrying away. And of course, we can then relate that to the frequency of our photon because E gamma is the same as H times F, where F is the frequency of the photon. So if we go ahead and solve for F, that's going to be E gamma divided by H, where that's Planck's constant. And this is something we can calculate. So E gamma is, what do we find it as? 6.153 mega electron volts. Okay, so mega is 10 to the 6. And then we can convert that to joules by multiplying 1.602, 10 to the minus 19. And so now we have the energy of the photon in joules. So if we take that and we divide it by Planck's constant, that's 6.626 times 10 to the minus 34. The units here are joules times seconds. So notice these units of joules cancel and we're just left with inverse seconds. Also remember, inverse seconds is just the same thing as hertz. Here's what we get. We get 1.49 times 10 to the 21 hertz. So that's an extremely high energy and high frequency photon. This would be like a gamma ray. And let's do another example with this 1D particle in a box. So for the n equals 1 state of a particle in a 1D box, what is the probability of locating the particle between x equals 0 and x equals L over 4? So let me just remind you how this works. We know what the wave functions for the 1D particle in a box look like, and we know how to calculate probabilities based on the wave function. The probability of locating a particle between x equals A and x equals B is just the wave function squared, so that's psi of x squared, integrated between x equals A and x equals B. So we're going to do that to this wave function. There's a follow-up question here, which is for the n equals 3 state, what is the probability of locating the particle in between x equals 0 and x equals L over 4? Okay. So in other words, what is the probability of finding the particle within the first 1/4 of the box for the n equals 1 state and for the n equals 3 state? So it turns out we're going to get different answers for the different n values. Let's go through it. All right, so what we're trying to do here is we're trying to calculate the probability that x is somewhere between xa and xb. And we're going to do this by calculating the integral from xa to xb of the wave function squared times dx. Okay, so in this case, I'm going to plug in the general form for our wave function. I'm not going to put in a specific value of n. And so what we'll have is the integral from xa to xb. And our wave function is the square root of 2 divided by L times sine of n pi x over L. And we're going to square that whole thing. And we'll pull out the constants. We have 2 over L, because we square the square root of 2 over L, so that's what we get. That's the constant that can be pulled out to the front. And then in the integral, we have from xa to xb, sine squared n pi x over L. Okay, so there's a little trick here that you can use to calculate the integral of sine squared, and it's to use a trig identity. So here's the trig ID that we're going to use. Sine squared of some angle theta is the same thing as 1/2 minus 1/2 times cosine of 2 theta. So this is useful because it's not clear what we should really do with sine squared, but if we just have a cosine, to the first power, then that's pretty easy to deal with. So we're going to make that substitution. So here's what that looks like. We have 2 over L, and then the integral from xa to xb. But now the function we're integrating is this. We have 1/2 minus 1/2 times cosine of 2 times the angle, which is n pi x over L. So now we have cosine of 2 times n pi x over L. So that's just what we get when we apply the trig identity to what's in the integral. And then, of course, we have our dx. Okay, so there is the trig ID. That's what it works out to. And now this is something that's not too bad to integrate. We can do it right away. So we have 2 over L. When we integrate 1/2, that becomes 1/2 x. So we have 1/2 x for our first term. And then we have, for our second term, minus 1/2 times cosine 2n pi x over L. Okay, when you take the cosine function and you integrate it, you get the sine function. But we have to do a little bit more than that. We have to multiply by this factor, L over 2n pi, to account for what's inside of the cosine function. So we have 1/2 times L over 2n pi, and then we have the sine after integration, again cosine becomes sine, of 2n pi x over L. And since we're evaluating this at the limits, that's evaluated between xa and xb. All right, so that's a nice general form that we can use to answer either of the questions. So for the first question, remember we have the n equals 1 state, and we're interested in the probability of locating the particle between xa equals 0 and xb equals L over 4. So the probability, I'll just call that P, for this to happen is, well, let's use the formula. It's 2 over L. And then in the brackets, we have 1/2 times x, where if we plug in the top limit, we're going to have L over 4 as our x value. Okay, and then the next term is minus, we have L over 4n pi, but n is just equal to 1. So I'll say 4 times 1 times pi. And then we have the sine. Okay, we have 2 times n is equal to 1, times pi. And then x is going to be L over 4. And then we're going to divide that by L. Okay, and then let's evaluate at the bottom limit. We have 2 over L. All right, and then I have 1/2 of x, but if I plug in 0 for x, that's going to give me 0. And like before, I have this L over 4 times 1 times pi thing. And then I have sine of blah, blah, blah times x, but the point is x is equal to 0, so I have sine of 0 there. So sine of 0 is equal to 0. That means this whole thing in the brackets is equal to 0. So I'm really interested in that first term. So let's take a closer look at that. What do I have? I have 2 over L. And then in this first term, I have L over 8 minus L over 4 pi. And what do I have overall? I have sine of, the L's cancel out. Overall, I have a factor of pi over 2. So I just have sine of pi over 2. Now, sine of pi over 2 is just equal to 1. So this is really just 2 over L times L over 8 minus L over 4 pi. So if I multiply the 2 over L into the brackets, I just get 1 over 4 and then minus 1 over 2 pi. So that's my probability. And if you calculate this, it comes out to 0.091. So there's about a 9% chance of finding the particle in the first 1/4 of the box for the n equals 1 state. But if we do the same thing for n equals 3, so we have n equals 3, xa equals 0, xb is equal to L over 4. Here's how the probability works out this time. So again, we're taking this expression right here, and we're evaluating between the limits xa and xb. So what do we have when we plug in the top limit? We have 2 over L, and then I have a half times x, which for the top limit is L over 4. And then here I have minus L over 4 times n. Now n is equal to 3, so this is 4 times 3 times pi. And then we have the sine of 2 times n, that's 3, times pi, and then x is L over 4. And then we divide that by L. So that's what I get in when that's what I get when I plug in the top limit. And then just like before, if I plug in the bottom limit of 0, I'm just going to get 0 out as a result. So I'll just say minus 0 for short. Okay, so what I have is 2 over L. And the first term is L over 8 in the brackets. The second term, what am I dealing with? I have L over 12 pi. And then I have the sine of what? So I have L's canceling out. I have 6 divided by 4. So that's 3 halves. Yeah. So I have the sine of 3 pi over 2. Yeah, there it is. And the sine of 3 pi over 2 is actually minus 1. The sine of pi over 2 over here was positive 1. That's what we did. But sine of 3 pi over 2 is minus 1. So actually we have 2 negative signs. We have an overall positive sign. We have 2 over L times L over 8 plus L over 12 pi, like this. So now let's multiply the 2 over L into the brackets. And now we have 1/4 plus 1 over 6 pi. And you can calculate that, and it works out to about 0.303. So in this state, there's about a 30% chance of finding the particle within the first 1/4 of the box. So it works out differently for the 2 different n values. Now, before we go on to the next example, I want to talk a little bit about superposition. Now, this is something that we saw way back when we were studying mechanical waves back in chapter 16, and it's going to be coming into play here again. So let's say that we have a set of wave functions, call them psi1, psi2, psi3, and so on. And every one of these wave functions is a valid solution to the Schrodinger equation. If that's the case, then any linear combination of these wave functions is also a valid solution. So for example, let's say that we have a particle in a 1D box. We can have the state psi of x, which is equal to c1, that's just some kind of constant, times sine of pi x over L, plus c2 times sine of 2 pi x over L, plus c3 times sine of 3 pi x over L. And that's just one example. There are a lot of others you could come up with. But what's going on here is you have a superposition of the n equals 1 state, that's happening over here, the n equals 2 state, and the n equals 3 state. So in general, a quantum system can be in any mixed state of different energies like this, okay? And we call this a quantum superposition. However, if you actually make a measurement of the energy of that state, it's always going to give you a definite value, right? It's not going to be some mix of energy 1, 2, and 3. You're just going to randomly get either energy 1, energy 2, or energy 3. You're going to get some definite value. So the idea is, prior to measurement, our system can be in a superposition of many different states. But when we make a measurement on it, the wave function collapses into some kind of definite state. So something pretty strange is happening here. Somehow, your quantum system can be in a superposition of many different states, but as soon as that system gets observed, as soon as you make a measurement on that system, that superposition is destroyed, and now you're just in a single definite state. So that's pretty weird, and to be honest, there's still a debate in the physics community about how to interpret this whole thing. So we'll just set that to the side for now, but we'll get back to it later at the very end of the lecture. But let's move on to something else. Let's move on to the harmonic oscillator. So we're going to start by going over the classical harmonic oscillator. This is what you learned back in Physics 45. And the sort of prototypical example that you saw was the mass spring system. So the idea is we have a spring, and the force constant of that spring is K, and connected to the end of that spring is some kind of mass. Usually we think of it as like a block, mass M. And of course, if we displace the spring from equilibrium, maybe we stretch it out, and then we let it go to set the block in motion, now it's going to be oscillating back and forth, okay? And we call that type of motion simple harmonic motion. So why does this all happen in the first place? Well, the spring exerts a restoring force on the mass, and that restoring force is given by Hooke's law. So the force that this mass is going to experience is equal to minus K times X. K is that spring constant from before. Remember, the higher the value of K, the stiffer the spring is. And then X is how much we displace the spring from equilibrium. The negative sign is just there to indicate that it's a restoring force. It brings us back to equilibrium. And so if you take this system and you set it in motion, it's going to start to oscillate back and forth at a certain frequency. And the frequency of that oscillation is given by omega. And omega here is actually an angular frequency, so we measure that in radians per second. So there's a nice formula for omega that you should remember from back in Physics 45. And it says omega squared is equal to K over M. So in other words, the frequency of the oscillation just depends on two factors. It depends on K, the stiffness of the spring, and it depends on M, the mass that's oscillating. So we can also take a look at this system in terms of energy. So first, let's think about the potential energy of the system. Basically, that comes down to the energy stored in this spring as a result of stretching it out or compressing it. That potential energy is given by this formula right here. U of x is equal to 1/2 kx squared. So this is what's called the spring potential energy. It's something you should know from back in Physics 45. And basically, in a nutshell, this says that the larger x is, the more energy we store in the spring. So in other words, the more we stretch out the spring or compress it compared to its equilibrium length, we get more energy stored in the spring. Okay, but if we look at our formula for the frequency, we can see that there's a nice substitution we can make for K, because K is equal to M times omega squared. So that allows us to rewrite the potential energy as 1/2 times M times omega squared times x squared. So that's the potential energy. Now, the total energy of the oscillator is not just that, it's the kinetic energy plus the potential energy. So the total energy, we're going to write that as E. That's equal to the kinetic energy, K, plus the potential energy, U. So that's the total energy right there. Now, there's a way of writing this total energy in terms of the amplitude of the system. Remember, amplitude represents the maximum displacement from equilibrium. So that's as far from equilibrium as the block ever goes in its motion. So if we think about the block oscillating back and forth like this, at the moment it hits x equals a, that's the maximum displacement, well, it's in the process of turning around, because right before it hit that point, it's moving to the right, and then exactly after that, it starts moving to the left. So for that brief moment when it's at x equals a, when it's at the maximum displacement, it's at rest, and it has no kinetic energy. So if we have no kinetic energy and all potential energy when x is equal to a, that allows us to write the total energy like this. It's 1/2 m omega squared times a squared. So this is a formula for the total energy. We're going to use that later. Okay. So all of that was a review of the classical harmonic oscillator. It's what you saw back in Physics 45. It's an oscillating system that we're analyzing using classical physics. But that's not going to cut it for us. What we want to do is describe oscillating systems on a microscopic scale. So, for example, maybe we want to study the vibrations of atoms in a diatomic molecule. Okay? If we're trying to do that, classical physics is not going to cut it. We're going to need to use quantum mechanics. So how do we do this? We're going to have to solve the Schrodinger equation. And we know what potential energy to use, fortunately, because for an oscillator, we know the potential energy is given by m times omega squared times x squared over 2. So we can use that. And if we plug that into the Schrodinger equation, we can solve for all the possible wave functions and all of the corresponding energy levels for what's called our quantum harmonic oscillator. So here's what the Schrodinger equation looks like. Remember, we have minus h bar squared over 2m times the second derivative with respect to x of our wave function psi of x plus 1/2 times m omega squared x squared. That's our potential energy, and that's multiplying psi of x. That equals E, that's the total energy of our particle, times psi of x. Now, actually solving this differential equation is pretty difficult, and it's beyond the scope of this class, so what I'll do is just quote the results. And here they are. We'll start with the energy levels. The energy levels are given by E sub n equals n plus 1/2 times h bar omega, where n can equal 0, 1, 2, 3, and so on. So these are integer values, but notice that 0 is actually included here. Now, of course, h bar, that's the reduced value of Planck's constant, and omega is the frequency that our system oscillates at. So the energy is dependent on the frequency that the system oscillates at. And because this is all multiplied by n plus 1/2, that means the energy levels are quantized. The quantum harmonic oscillator can't just take on any energy value. It can only take on discrete energy values. So we're seeing that come into play once again. The wave functions get a little bit complicated, so I'm just going to describe what they look like. The corresponding wave functions for the energy states, let's say energy state n, is a normalization constant multiplied by a Gaussian multiplied by a Hermite polynomial. So let's see what that looks like. We have our normalization constant. That's what I'm labeling as n sub n. That's the normalization constant. The Gaussian part is this. It's e to the minus 1/2 beta squared times x squared. So the shape of this function is like a bell curve. You've probably seen that sort of thing before. Now, beta is just a collection of different constants to make this a little bit more compact. Beta is equal to the square root of m omega over h bar. Okay, so this last little bit, h sub n, is called our Hermite polynomial. So what we're plugging into this Hermite polynomial is beta times x. So that's what we're plugging in. And I'll just list the first three Hermite polynomials for you so you can get a sense of what they look like. H sub 0 is really simple. That's just equal to 1. So in the case of the n equals 0 state, this last term is just equal to 1. H sub 1 is equal to 2y. So for variable, for our polynomials y, this would just be 2 times y. H2 is 4y squared minus 2. And there's a whole list of these, but to be honest, we're not really going to go beyond the first three, so those are the ones we'll need to know for now. All right, so let's see what some of these wave functions look like when we plot them out. There's a lot going on this graph here, so let me just take it piece by piece. So in the black curve, what we have is u of x. That's the potential energy of our oscillator as a function of position. So on this axis, going horizontally, we have x. So remember, the potential energy goes like x squared. It's proportional to x squared. So we expect the shape here to be a parabola, a concave up parabola. Okay, then our ground state wave function, that's psi sub 0, that's shown in red here. And this just looks like a bell curve. There's a single peak right at x equals 0, and then it just decays away as x goes to positive infinity in this direction and negative infinity in that direction. All right, if we look at the first excited state, that's psi 1, that wave function is shown in blue. Now this one has a trough on the negative side and then a peak on the positive side. And then it asymptotically goes to 0 as x gets really big in either direction. Okay, and then the second excited state, psi 2, it's a similar sort of thing, but now we have a peak on this side, and then we go to a trough right in the middle, and then another peak on the positive side. And then, of course, n can be arbitrarily big. There's a whole bunch of other wave functions. In fact, there's an infinite number of possible wave functions, because n can have any integer value, these are just the first three to give you a sense of what they look like. So this is the general form. Okay, you can plug in any n value, and this is the general form. Down here, and these are color-coded to match the curves on the graph, these are the specific cases for n equals 0, n equals 1, and n equals 2. So there's two things I'm going to claim up here about these wave functions. For any energy state, doesn't matter if we're talking about the ground state or n equals 1 or n equals 2 or n equals 3, the expectation value for both position and momentum are going to be 0. Okay, so in other words, the particle can be located at various different positions, but on average, it's going to be located at x equals 0. So it spends just as much time over here at positive x values as it does over here at negative x values, so that the average works out to x equals 0. And then the same thing goes for momentum. The momentum expectation value is also 0. That means your oscillator spends just as much time traveling in the positive x direction as it does traveling in the negative x direction. So it has positive momentum sometimes, it has negative momentum other times, and it all averages out to 0 momentum because it doesn't have any sort of preference for moving to the left or moving to the right. So what I'm going to show you is that the expectation value for position does come out to 0, at least for the n is equal to 0 state. It's kind of hard to prove this in general, so we'll just take a look at this one specific case. So the wave function for the n equals 0 state, that's what we call the ground state, is equal to beta squared over pi, taken to the 1/4 power, times e to the minus beta squared x squared over 2. That's just our wave function. And then remember, we can calculate an expectation value based on the wave function. So the expectation value for x is the integral from minus infinity to positive infinity of x times psi of x squared. Now, if the wave function had complex values, we'd have to worry about psi of x squared. We'd have to take the complex conjugate, multiply it by the wave function. But in this case, the wave function here doesn't have any complex numbers in it, doesn't have I in it, right? So we can just square it, and that's it. So what happens when we do that is we have the integral from minus infinity to infinity of x, and then we have beta squared over pi to the 1/4 power times e to the minus beta squared x squared over 2, and then we're squaring that whole thing times dx. Okay, now beta and pi, those are all just a bunch of constants. And if we take the 1/4 power and we square it, it becomes the 1/2 power. So pulling that as a one big constant out, we have beta squared over pi to the 1/2 power. Then what's left in the integral is we have minus infinity to infinity, x times e to the minus beta squared x squared. Because when we combine the powers here, we basically multiply them together, and that factor of 2 goes away. So that's what we are left with. And then don't forget there's a dx there. Okay, so I just have to evaluate this integral. And it's actually not too bad. This is a case where we can use a u substitution. So what we're going to do is let u equal beta squared times x squared. So basically the thing in the exponent is going to be u. And if we take the derivative of that, du dx, what that equals is we have 2 beta squared times x. All right. So if I rearrange that, I can say x times dx is equal to du divided by 2 beta squared. And that's nice because in the integral, I have x times dx. All right, so I'm first going to just do the indefinite integral without plugging the limits in. And then once we have the result, we'll deal with the limits, okay? So here's what we're dealing with. We have e to the minus u, and then the x dx part, like I said, is du divided by 2 beta squared. And 2 beta squared is a constant, so I'll just pull it out. It's 1 over 2 beta squared times integral e to the minus u du. So that's actually a very simple integral to do. It just works out to, so I'll write the constant out front, 1 over 2 beta squared. E to the minus u becomes minus e to the minus u when you integrate it. All right, so let's go back to our original expression in terms of x. So what did we have? We had this constant beta squared over pi to the 1/2 power. But when we made the substitution, we introduced this new constant 1 over 2 beta squared. And then we had minus e to the minus u. But I'm just going to put back that u is equal to beta squared x squared. So I'm just going to re-substitute x as our variable, like this. All right, so then we're going from what limits? Minus infinity to infinity in terms of x. Those are the limits. And so what do we have? We have minus beta squared over pi times 1/2 times 1 over 2 beta squared. That's the overall factor out front. And then I have e to the minus beta squared x squared. But for my top limit, I'm plugging in infinity for x. So, okay, if I plug in infinity for x, my exponent becomes minus infinity. And then I have to now subtract what I get when I plug in the bottom limit. My bottom limit is x equals minus infinity. But if I square that, well, the negative sign goes away. So it's like plugging in, infinity right here. And there's already a negative sign right there. So this is like e to the minus infinity overall. So what do I have? E to the minus infinity, that's actually just going to 0, and then minus e to the minus infinity, also going to 0. So forget all those constants out front. It doesn't matter what they are. The result is just 0. Okay, so I've shown you that the expectation value for position is equal to 0, at least for the ground state wave function. But again, it's more generally true. Now let's take a closer look at the energy levels for our quantum harmonic oscillator. So in this diagram, we're showing energy on the vertical axis and position on the horizontal axis. And like before, this black curve is going to represent the potential energy of our oscillator. Now these red curves are going to represent the total energy. That's kinetic plus potential. That's what we're calling E for the oscillator. And that can take on different values. So let's just see what happens when we plug in different values of n. So the lowest value of the n we could plug in is 0. That's what we get when we're in the ground state. So in that case, E0 is going to be 1/2 h bar omega. So that's what we call our ground state energy. That's the lowest possible energy value, 1/2 h bar omega. So that's our energy right here, E0. If we plug in n equals 1, what we're going to have is 1 plus 1/2 times h bar omega. That's 3/2 times h bar omega. So that's E1. That's the next energy level up, 3/2 h bar omega. Plug in n equals 2. You're going to get 2 plus 1/2. That's 5/2 h bar omega. So that's E2, 5/2 h bar omega. And you can keep going. The next one would be 7/2, 9/2, and so on. But notice the gap in between the energy levels is always just h bar omega, right? So if I go from n equals 0 to n equals 1, the gap is h bar omega. If I go from n equals 1 to n equals 2, the gap between those energies is h bar omega. So we can call that gap delta E, and that's just equal to h bar omega. All right, so the energy levels are evenly spaced for the quantum harmonic oscillator. That's what's happening here. So let's do an example. So we have an HCl molecule. HCl is a diatomic molecule consisting of one chlorine atom and one hydrogen atom. Because the chlorine atom is 35 times more massive than the hydrogen atom, the vibrations of the HCl molecule can be quite well approximated by assuming that the Cl atom is motionless and only the H atom moves. Okay, so when we're picturing the vibration of the molecule, you want to think of it something like this. You have two atoms, each one is a little point mass, and the spring in the middle of them is not an actual spring, of course, but it just represents the bond between the two atoms, the chemical bond between them. And the distance between the two atoms can change over time, right? They can get closer together, further apart. And when that happens, the molecule vibrates, okay? So for the case of the HCl molecule, we're assuming it's only the hydrogen atom that's moving any significant amount, and the Cl atom is motionless because it's so much more massive. Okay, so that's the preface. So here's some data. The vibrational spectrum for HCl has the lowest frequency line centered at 8.88 times 10 to the 13 hertz. So what we mean by this is the type of light that's given off by HCl molecules, the type of photons that are given off, have the lowest frequency at 8.88 times 10 to the 13 power hertz. So that's what we know. So the question is, what is the spacing between the vibrational energies of this molecule? So that's the delta E from before. What is the force constant K of the atomic bond in the HCl molecule? And then what is the amplitude of the vibrations for the ground state? That's n equals 0. And the first excited state, that's n equals 1. So let's work this out. So the first thing to remember is that when an atom or a molecule makes a transition between energy states, it does so by either emitting a photon or absorbing a photon. So if we apply conservation of energy to this type of process, what we have is the energy of the emitted photon is equal to the change in energy of the oscillator. That's our molecule in this case. Okay, so let's think about what is the lowest energy photon that our system can actually emit. That's going to happen when we're transitioning between neighboring energy levels, okay? Because if we're transitioning between energy levels that are really far apart, okay, then the change in energy of our oscillator is going to be really big, and the energy of our emitted photon is going to be really big. If the change in energy of our oscillator is really small, then the energy of our emitted photon is really small. So how do we get the smallest possible energy for the emitted photon? It's when we're transitioning between neighboring energy levels, okay? So for example, going from n equals 2 to n equals 1. All right, so let's just write that down. The lowest possible energy for the emitted photon that's going to happen when we're transitioning between neighboring energy levels. And again, the example I give here is like going from n equals 2 to n equals 1. Okay, so let's write down an equation now. The energy of our emitted photon is HF. And the change in energy of our oscillator is, I'll just call that delta E. That's the gap between neighboring energy levels that I showed you before. We can write down what this is. Delta E, the gap between energy levels, is just H times F, where F is that frequency of this photon that gets emitted. So we have 6.626 times 10 to the minus 34 joules times seconds for H. And then for F, we have 8.88 times 10 to the minus 13. I'm sorry, that's not minus 13. That's 10 to the positive 13 hertz, which is the same as inverse seconds, okay? So in joules, this works out to 5.884 times 10 to the minus 20. And we can convert this over to electron volts because 1 electron volt is the same as 1.602, 10 to the minus 19 joules. All right, so what does this work out to? It's 0.3673 EV. And to keep 3 sig figs on that, we have 0.367 EV. So to recap, if this is the frequency of the lowest energy photon that gets emitted, this must be the spacing between our energy levels. Okay. So the next thing is we want to solve for K. That's like the force constant for the bond between the two atoms. So for this, we're going to write delta E is equal to h bar omega, where here what we're saying is the spacing between energy levels for our oscillator is equal to h bar times omega, where omega is the frequency of our oscillator. How fast is it oscillating? Well, omega, if you recall, is the square root of k over m. So we're going to plug that in for omega. And we're trying to solve for k, so if we square both sides, we have delta E squared equals h bar squared, and then the square root goes away, we have k over m. So again, I'm trying to solve for k. K is equal to m times delta E squared divided by h bar squared. So we can plug in the numbers. So m is the mass. That's going to be the mass of our hydrogen atom. That's the only one that effectively is moving. And that is 1.67, 10 to the minus 27 kilograms. All right, delta E is what we just found. That's 5.884, 10 to the minus 20 joules. So I want to use the SI unit of joules here because that's equivalent to a kilogram meter squared per second squared. And then I'm going to go ahead and divide that by h bar squared. So remember, h bar is 1 over 2 pi times h, where h is 6.626, 10 to the minus 34. Units are joules times seconds, but if we expand that out, that's kilograms meters squared per second. Okay. So what are we left with as far as the units go? It looks like meters cancel. We have one factor of kilograms on top and seconds squared on the bottom. And the numerical value that you should get is 519.9. But we want to keep 3 sig figs on that at the end of the day. Let's take a closer look at the units for a second. So for a spring constant, we expect the units to be newtons per meter. And if we break that down a little bit, a newton is the same as a kilogram meter per second squared. And if we divide that by meters, then we see that meters go away. And we just get kilograms per second squared, which is the unit that we came up with in this calculation. So at the end of the day, this comes out to about 520 newtons per meter. Now that's a lot. I mean, if you remember the springs lab we did back in Physics 45, those springs had, K values of like 10 newtons per meter. So for a molecule to have a K value this large is pretty impressive, actually. So anyway, let's do the next part. The next part, we're finding amplitudes, okay? So here we go. Let's calculate the amplitudes. The energy of our oscillator, E sub n, is equal to n plus a half, and then we're going to multiply that by h bar omega. But remember, the energy of an oscillator can be written in terms of the amplitude like this. It's 1/2 m times omega squared times a squared. So if we want to solve for the amplitude, we just have to solve for a. So what do we get when we solve for A? Well, let's start by just saying A squared is equal to what? It's going to equal 2 times n plus a half times h bar divided by m times omega. And actually, remember that omega is the square root of k over m. So I'm going to make that substitution. So on the bottom, we have the square root of k over m. And we can simplify this a little bit more. So on top, we have the same thing as before. On the bottom, we can write this as the square root of m times k. When you bring this m into the square root, that's what it works out to. All right, so those are all numbers that we can plug in because we know m and we know k. We just found that. And we can plug in different n values for the different energy levels. All right. So here's what it works out for the n equals 0 case. Okay. So for n equals 0, here's what we have. A equals, we have to take the square root of this expression because we solve for a squared. So we have the square root of 2 times 0 plus a half. And then we have h bar, where h bar is 1 over 2 pi times h, which is 6.626, 10 to the minus 34. And the units are the same as before, kilograms, meters squared per second. Okay, and then we divide that by the square root of m times k, where m is 1.67, 10 to the minus 27 kilograms. And k is 519.9 kilograms per second squared. All right, so that's the calculation we have to do. And the amplitude that you get is 1.06, 10 to the minus 11 meters. So that's for the ground state. That's the amplitude of the vibrations of this molecule when it's in its lowest energy state. Okay? If you do this same exact calculation, but you plug in n equals 1 instead, so the only difference is right here, we're going to plug in 1 instead of 0. Okay? This is what you'll get. You'll get that the amplitude is equal to 1.84 times 10 to the minus 11 meters. So that's interesting. You can vibrate with this amplitude, and in the next energy state, you can vibrate with this amplitude, but you can't have any amplitude in between. So not only are the energies quantized, but so are the amplitudes. All right, so here's one for you to try out. The vibrational frequency of the hydrogen iodide, that's the HI, diatomic molecule, is 6.69, 10 to the 13 hertz. So that's the frequency of the molecule's vibration. What is the energy of the emitted photon in EV when this molecule makes a transition between the n equals 3 and n equals 0 vibrational energy levels? And then what is the frequency of this photon in hertz? What is the wavelength of this photon in meters? So some numbers you'll need to know are Planck's constant and the conversion between electron volts and joules. I also gave you the formula for the energy levels of the quantum harmonic oscillator. That's going to be used as well. So pause the video, try to work this out, and then we'll go through it together. Okay, so we'll start by writing down the energy of our ground state, which is 0 plus a half times h bar omega, because we're plugging in n equals 0. So that's just a half h bar omega. The energy of the n equals 3 state is 3 plus a half times h bar omega, which is the same as 7 halves h bar omega. So we're going from n equals 3 to n equals 0, and those are the energy levels. So remember, the energy of the emitted photon is equal to the change in energy of the oscillator. So what we'll say is E gamma, I'll just write that as the energy of the photon, is E3 minus E0. That's the change in energy that the oscillator undergoes. And so that's going to be 7 halves h bar omega minus 1 half h bar omega. That's 6 halves or 3 times h bar omega. Okay. So I'm going to rewrite this slightly. I'm going to remind you that h bar is just h over 2 pi, so it's Planck's constant over 2 pi. And also omega is 2 pi times f. So what we're given is a frequency f, so that's why I'm making the substitution. So 3h bar omega is the same as 3hf. So we can calculate that. We have 3 times h, which is 6.626, 10 to the minus 34 joules times seconds. And then for f, remember that's the frequency of the vibration of our oscillator, which is 6.69 times 10 to the 13 inverse seconds. All right, so this works out to joules. We get 1.3298, 10 to the power minus 19 joules. And to convert this over to EV, electron volts, remember 1 EV is the same as 1.602, 10 to the minus 19 joules. Okay, this works out to 0.830 electron volts. So the photon that gets emitted has that much energy. Okay, so next, let's calculate the frequency of this photon. So here I'm going to write the formula for the energy of a photon. E gamma is h times f. Now, this might seem a little confusing because we wrote down hf over here. Previously, we were referring to f as the frequency of the vibration of the oscillator. Here, I want f to mean the frequency of the photon, so I'm gonna label it differently. I'm gonna label it as f gamma, okay? So I'm gonna find f gamma. That's equal to E gamma over h, and we can just directly plug in the numbers. We have 1.3298 10 to the minus 19 joules. And then h is 6.626 10 to the minus 34 joules times seconds. So what we'll get is a frequency which is measured in hertz. And this will come out to 2.007 10 to the 14. And the units are inverse seconds, but remember that's the same as hertz. So to round it off, it's like 2.01 10 to the 14 hertz. All right, last we're going to do the wavelength. So for the wavelength of the photon, we're just going to use the fact that c, the speed of light, is equal to lambda times f. And that allows us to solve for lambda, the wavelength. That's c over f, or 3.00 10 to the 8 meters per second, divided by 2.007 10 to the 14, and the units are inverse seconds. So seconds cancel, you just get meters. And this comes out to 1.49 times 10 to the minus 6 meters. All right. If we convert that to nanometers, that's actually 1,490 nanometers, which is the infrared part of the spectrum. So in general, when you have vibrating molecules making transitions from one energy level to another, they typically emit in the infrared part of the spectrum. And that's what we're seeing here. So the last thing we'll go over today is a comparison between the quantum harmonic oscillator and the classical harmonic oscillator. So for the classical harmonic oscillator, the amplitude can really take on any value. Okay, it has a continuous range of amplitudes it can take on. There's no restriction on what A can be, right? And for that reason, the energy can also take on a continuous range of values because the energy is related to the amplitude by 1/2 m omega squared times a squared. But in the case of the quantum harmonic oscillator, the energy levels are discrete, right? You can only take on certain values of energy, and there are gaps in between those where there are forbidden energies that you can't have. And the same goes for the amplitude, right? The amplitude can only take on certain discrete values as well, with gaps in between. There's one other feature of the quantum harmonic oscillator that I want to point out before we end this. It's that a quantum harmonic oscillator can go outside of the range x equals minus a to x equals positive a. Now, think about what the amplitude means for a classical harmonic oscillator. It means we're going back and forth. We're oscillating back and forth around some kind of equilibrium position. And the furthest we ever get from our equilibrium position is A. So of course, we can't get to a value of x that's larger than A, right? Because A is the maximum value of x. That's why we're saying you're sort of restricted to this range, x equals minus A to x equals positive A, right? For the quantum harmonic oscillator, that's not the case. There is some probability that a quantum harmonic oscillator can be found outside of this range. In other words, the wave function has non-zero values outside of this range. So this is just the first example we're going to see of a quantum system where it can take on positions that are forbidden classically. It can be located in positions that are forbidden classically. And we're going to see that in the next video when we go over quantum tunneling, okay? But we'll end it here for now.